Не мог бы кто-нибудь сказать или написать мне e-mail, значит, с описанием, чего не хватает? И, значит, мы попробуем там посмотреть всякие там жесткие диски и выяснить, где находится то, значит, то, чего не хватает.
Не хватает только первой части первого занятия.
Хорошо, ну, будем искать. Так, значит, я правильно понимаю, что все уже, значит, запустилось и... Так, значит, запустилось, не запустилось, запустилось. Okay, so today we'll talk about the Hajj decomposition theorem, and we'll deduce this theorem from two more simple theorems on elliptic operators, which we will prove later. And okay, so I will state a few theorems about not too many, just two, about elliptic operators, and then we'll use those theorems to prove the Hajj decomposition. Well, the first theorem is something we already mentioned a few times, but let's mention it again. Well, here E, F are smooth vector bundles. Over a compact, smooth manifold without boundary. Let's call the manifold, let's call it X. And we'll let's introduce smooth Riemannian metrics on both bundles. Well, the first claim is both the kernel and the co-kernel of the operator are finite dimensional, and it's essential here that the operator is elliptic. Otherwise, it's none of this is true. I would like to also recall that operators which have these two properties are called Fredholm. And another important thing is that the image of D is closed and complementable. Closed with respect to which topology, and complementable in which sense? Well, since we have metrics, we on both manifolds we can equip the spaces of sections with a scalar product, which is positive definite. But the resulting metric space is not necessarily complete. But still, it makes sense to talk about closed subspaces and complementable subspaces, and the claim is that the image of D has both these properties. Now, theorem 2. Suppose we have just one vector bundle over a smooth compact manifold without boundary. And suppose we have a self-adjoint elliptic operator, self-adjoint with respect to some Riemannian metric Oni. And then this operator has a kind of inverse. In other words, there exists an operator called the green operator, and it goes from, well, again, from sections to sections. Such that okay, such that we have this equality. Now, well, it's clear what this means and what this means. But what is this? I is the identity, and what is PRH? H is the kernel of D. By theorem 1, we know that this kernel is finite dimensional. Now, if we have a finite dimensional subspace of a Prey-Hilbert space, it still makes sense to consider the orthogonal projection onto this subspace. And basically, we could use the familiar formula from linear algebra. Yes, and this PR is the orthogonal projection. The orthogonal projection to H. And well, in the most basic example, H is the space of harmonic forms. Hence the letter H, but the same well, the same space with similar properties can be defined for an arbitrary self-adjoint elliptic operator.
Is H complementable?
H well,
When you talk about projection H.
Yes, H is complementable. Why? Actually, we saw last time. Okay, let's well, let's erase this part and try to remember one of the things we saw last time. So if If I have an operator from one Prey-Hilbert space to another Prey-Hilbert space, then does anyone remember what we proved about the kernel of? Suppose we have an operator such that there is an adjoint, and then we proved a very simple equality about kernels, images, and the orthogonal complements. Now, what exactly was this equality?
Kernel of adjoint is the complement of image of. Is the complement of image.
Okay, so we proved this equality. Now, suppose H1 and H2 are the same, and suppose A star and A are the same. Now, what does this what does this tell us? This tells us that the kernel of the kernel of A is the orthogonal complement of A of the image of A. We know that the image is complementable. Why? Well, because the operator is elliptic, so we can apply theorem 1. Okay, what does this mean? Well, this means the image plus the orthogonal complement is the whole space. Well, the image is complementable, hence the orthogonal complement is complementable. Okay. Now, these are two theorems which we will prove shortly, I hope, but then they're not for free. And to prove those theorems, we'll need to talk a little bit about analysis and well, it'll take us some time, but we'll get there eventually. Now, are there any questions, comments, or criticism? Okay. Now I will raise those theorems and then we'll see another theorem which is more closely related to topology, and we'll deduce this other theorem from these two. And by the way, last time we talked about elliptic complexes. Does everyone remember what those are? Okay. Do we or do we not need a reminder on elliptic complexes? Okay, I'll give a short reminder. An elliptic complex is a sequence of, well, like the one shown on the blackboard, where each di is a differential operator. We assume that all those operators have the same order, and we also assume that the sequence is a complex, meaning the composite of two consecutive arrows is 0, and the sequence of the symbols is exact, and that's where we need this assumption on the order, because otherwise we can't compose the symbols. And one example is the Theorem operator, Theorem complex, where we just take the differential forms on a manifold and the Theorem differential as D. And there are quite a few more examples which have this form, and these are relevant to topology. In particular, there is another example which of a similar type, which calculates the signature of a manifold. Does everyone know what the signature is? For which manifolds is the signature defined? Oh, for which manifolds is the signature interesting? It can be defined for all manifolds, but for most manifolds it's not particularly interesting, but for some it is.
Dimension 14.
Yes, when it's only interesting for manifolds of dimension divisible by 4, but then it really is interesting. Well, and it's an important invariant, and comes up in many questions, surgery, for example, and some other questions as well. Yes, so there is an operator which such that the index of this operator is the signature, and there is another operator. There is another elliptic complex such that the resulting cohomology groups are the are isomorphic to the cohomology groups of vector bundles on complex analytic manifolds. And if our manifolds are compact, so if X is algebraic, these complexes will calculate the cohomology of the corresponding coherent sheaf. Okay. Okay. Now I will state the Hajj decomposition theorem. Well, suppose we have an elliptic complex. On a smooth compact manifold without boundary, and suppose all bundles involved here have been equipped with A or with Riemannian metrics. So, in particular, it makes sense to talk about taking the joint. Then I take I set D equal small d plus the conjugate. Sorry, plus the joint. Then the square is called the square of D is called the Laplacian operator. And since we have d squared equals 0, d adjoint squared is also 0, and when I expand the expression, the only two remaining terms are these, okay. What else do I need? I think this is it. Well, the first statement is something we already saw last time. Now, the first statement is that the kernel of D is the same as the kernel of delta, which is what we saw last week, no, 2 weeks ago. And well, the second equality is straightforward. Because the Laplacian operator preserves every space here. D doesn't. D mixes everything up. But the Laplacian operator preserves everything. So we have this this equality for kernels. And the next equality is just automatic from the fact that this kernel is equal to this kernel. Well, let me mention a small corollary, which is also automatic, but will need it. D and the conjugate of D are both 0 on the kernel of D, and this is not at all clear from the definition.
Why is it clear?
Well, because I have this decomposition. Okay, more precisely, I have this decomposition. If I want to check this formula for all elements of the kernel of D, I only need to check it on each individual homogeneous component. Okay. Well, this vector space is important, and let's call it. Let's denote it by H. And it's the space of harmonic elements. Harmonic, why harmonic? Well, because in the classical case, these are precisely the harmonic forms. Well, I've turned it on. Well, it looks like we need new batteries. Okay. Well, those things happen. Okay, I'll try and go. Try and find new batteries. By the way, if by any chance someone already has new batteries, let's. Okay. Okay, so let's make a short break while I'm looking for batteries.
Но звука действительно не было.
Не, ну красный, как может быть?
Видимо, с камеры звук записывается.
Значит, очень тихо.
Do you understand why that map is a co-chain map?
No.
Looks like it's working. Okay. Yeah, let's continue. Well. Yes, so we have something which looks like a chain homotopy. A chain homotopy between which two maps? Well, one of the maps is the identity, which is clearly a chain map, and the other one is the projection. We don't know yet whether or not it's a chain map. But let's see. Let's look at this formula. Let's look at this formula. D dg d star plus g d star d is d g d d star. Okay. And then let me compose in the reverse order d g d star plus g d star d, and then d. Well, this time I get d squared on the right, and the result is d g okay. So it's not working out, but let's see. We have a blah, blah, blah,
The
blah,
first
blah.
line, we need to swap d with d star.
In the first line, we need
After quantity sign.
yes, there's a mistake here. Okay, so yes, so the results are the same. So the consequence is the orthogonal projection is a chain map. And this map is chain homotopic to the identity. Why? Well, basically by this formula.
That is implied that H star is a kernel of D.
No, but it does. It is contained in the kernel. There are many other elements in the kernel. It could be. Okay, so the main ingredient is this identity, which is a consequence of theorem 2. Well, sorry, 1, 2, 3. every part 3 is what people often call the Hajj decomposition theorem, but it follows from straight from part 2, and it says that every cohomology class of this complex has a unique harmonic representative, meaning a unique representative which belongs to H star. Now, there's one thing which I don't like here. Normally, if I have a co-chain complex, I need to write the star on at the top, not at the bottom. But well, I already started using E with a lower I last week, so let's just grin and bear it. E lower star. Although the differential increases the degree. It's bad notation. Okay, every cohomology class has a unique harmonic representative. Are there any questions, comments, criticism? And part 4, I'll try to squeeze it here. Well, part 3 follows from part 2, so there's we don't need an extra any extra effort to prove part 3. Now, part 4. In the sequel, we will need to consider the even and odd component of D separately for various reasons. Okay, I don't want to okay, so okay, let me take the operator D, which is small d plus small d adjoint. Let me take the direct sum of the restrictions of those to the even components, and similarly d minus the restriction to the odd components is denoted d minus. So so we have So we have d plus, which goes from the sum of the even components to the sum of the odd components, and d minus, which goes the other way around. Last time, not last week, 2 weeks ago, we saw that these two operators are the adjoints of each other in the following sense. Recall that we equip each bundle with a metric. Then we take the direct sum metric on the direct sum of the bundles, and then it makes sense to talk about adjoints, and we do, and one of each of the operators is the adjoint of the other. And I don't remember whether or not we did this last time, but let's do this now anyway. My claim is that both operators are elliptic. Why? Well, let's try to remember how we proved that D is elliptic. Well, basically, there are several ways to prove this, but the easiest way would be to handle the Laplacian operator first, and then deduce that D is elliptic. But then we can use the same trick for D plus and D minus. If I take D plus and D minus and I square each of these, what do I get? I simply get the sum of the even components of the Laplacian and the sum of the odd components of the Laplacian respectively. And all components of the Laplacian are elliptic. Now the formula, both operators are elliptic, so it makes sense to, and as a consequence they have Fredholm. It does make sense to ask whether the indices are related, and they are related. Namely, one is minus the other. And this is something which we, I think, saw last time in a slightly more general form. Basically, the statement was, suppose I have two Prey-Hilbert spaces and an operator from the first to the second, such that the adjoint exists, and both the operator and the adjoint operator have the images which are closed and complementable. And then the index of the adjoint operator, and suppose both operators are Fredholm. And all these assumptions are applicable precisely because D plus and D minus are elliptic. So we may apply the statement we proved last week, no, last time, and we get this. We get this equality. Okay. Now, now we have deduced the Hajj decomposition theorem. Of course, we haven't proved any of the theorems. Any of the main theorems, but we will do this at some point. What remains is this lemma, and I suggest we have a break, and then after the break we will prove this lemma. It's well, it looks innocuous, but in fact this lemma requires some work. So it's not completely for free. Are there any questions? Okay, then I think we let's have a break until let's say 10 past 6.
Okay, maybe I have a question. Where is the decomposition? It's called the Hajj decomposition.
Well, the decomposition is everything is the kernel of H. Sorry, the kernel of the Laplacian plus the orthogonal complement, and as we saw in after theorem 2, the orthogonal complement is the same as the image. Okay. Are there any more questions? Okay, then I'll turn this off and